When someone says dark matter is evil, I know what they usually mean. They mean it is invisible. It does not shine. It does not help us the way stars and gas help us. It makes galaxies rotate too fast. It bends light in ways that confuse our intuition. It dominates the mass budget of galaxies and clusters, and it refuses to show up in our detectors, so it feels like an enemy. But in physics, evil is not a property. Dark matter is not trying to hide. It is not malicious. It is simply matter that interacts very weakly with light, and possibly very weakly with ordinary matter, while still responding to gravity. The real story is not moral. It is about how gravity shapes space-time, how expansion stretches space, and how the universe builds structure from tiny early ripples into the cosmic web we see today. Let me start with what we actually observe. In spiral galaxies, stars orbit the center. If most of the mass were in the bright disk and bulge, the orbital speed should drop with distance, the same way planets slow down farther from the sun. But when we measure rotation curves using starlight, and even better, the 21-centimeter radio emission from neutral hydrogen, we see something else. The speeds stay roughly flat far beyond the visible edge. That means the enclosed mass keeps increasing with radius, even where there is little light. The simplest explanation is a large extended halo of unseen mass. This is not a small correction. In many galaxies, the dark component outweighs the stars by a factor of several, and in small dwarf galaxies it can dominate even more strongly. Then there are galaxy clusters. We can estimate their mass in several independent ways. We can use the motions of the galaxies inside the cluster. Faster motions require more gravitational binding, so more mass. We can also use the hot intracluster gas, which glows in X-rays. That gas sits in the cluster's gravitational potential well. Its temperature and pressure profile tell us how deep the well is, and we can use gravitational lensing, which is the most direct in a certain sense, because it does not care whether the mass is hot, cold, bright, or dark. Mass curves spacetime. Light follows the curved geometry. If a cluster sits between us and distant galaxies, it distorts their shapes and shifts their apparent positions. By mapping those distortions, we can reconstruct the mass distribution. All three methods agree on the same basic conclusion. There is far more mass than we can account for with stars and gas. One of the cleanest demonstrations is in colliding galaxy clusters, where the different components separate. In a collision, the galaxies themselves mostly pass through each other because they are small compared to the distances between them. The hot gas, however, interacts electromagnetically. It feels pressure and shock. It slows down and can lag behind. If most of the mass were in that gas, the gravitational lensing signal should follow the gas. But in famous systems like the bullet cluster, the lensing mass peaks line up more closely with the galaxies, not with the shocked gas. That strongly suggests that most of the mass is in a collisionless component, something that goes through with the galaxies and does not get dragged by electromagnetic forces. That is exactly what we mean by dark matter in the standard picture. Now, it is important to be honest about what this does and does not prove. It proves there is extra gravitational mass beyond the luminous matter, and that it behaves approximately like a collisionless fluid on cluster scales. It does not by itself tell us the particle identity. It also does not mean gravity must be exactly Einstein's general relativity on all scales, though general relativity has passed many tests. There are modified gravity ideas that try to reproduce galaxy rotation curves without dark matter. But the full set of observations across many scales and epochs is difficult to match without some non-luminous matter component. The strongest overall fit comes from what we call the lambda CDM model. Lambda stands for dark energy, modeled as a cosmological constant. CDM stands for cold dark matter, meaning the dark matter particles were moving slowly compared to the speed of light when structure began to form, so they could clump efficiently. If you want to understand why dark matter is so central, you have to go back to the early universe. The cosmic microwave background is the afterglow of the hot early plasma, released when the universe cooled enough for electrons and protons to combine into neutral atoms. Before that moment, light was trapped, constantly scattering. The plasma supported sound waves, driven by the competition between radiation pressure pushing outward and gravity pulling inward. Those waves left an imprint as temperature fluctuations in the microwave background. We measure them with satellites like DUMMAP and Planck. The pattern is not random. It has peaks at specific angular scales, and those peaks encode the amounts of ordinary matter, dark matter, and dark energy. Here is the key point. Ordinary matter interacts with radiation. Dark matter, in the standard view, does not. So in the early universe, ordinary matter was tied to photons and felt radiation pressure. Dark matter could start clumping earlier, creating gravitational wells. When the plasma finally became neutral and photons decoupled, the ordinary matter could fall into the existing dark matter wells. That helps explain how we get large galaxies and clusters by the time we observe them, without requiring the initial fluctuations to be implausibly large. The microwave background also lets us infer the total matter density and the baryon density separately. The baryon density also agrees with Big Bang nucleosynthesis, the early formation of light elements like deuterium and helium. Put these together and you get a consistent picture. Only about 5% of the present-day energy density is ordinary matter, about a quarter is dark matter, and most of the rest is dark energy. The exact numbers depend on the dataset and assumptions, but the broad result is stable. So where does evil come in? Often it comes from the fact that dark matter seems to dominate outcomes. It acts like an invisible scaffold. It dictates where galaxies form and how they move. It can make galaxies tear each other apart through tidal forces. It can deepen gravitational potentials so much that gas heats to tens of millions of degrees in clusters. But these are not acts of cruelty. They are consequences of gravity. Gravity is not a force in general relativity in the usual sense. It is geometry. Mass energy tells spacetime how to curve, and curved spacetime tells matter and light how to move. Dark matter contributes to that curvature. So it shapes trajectories, it bends light, it changes the rate at which structures grow. If you remove dark matter from the equations, the universe still expands and gravity still acts. But the timing and the architecture of structure formation change dramatically. There is another reason people call it evil. Dark matter is hard to catch. If it were made of ordinary atoms, it would absorb and emit light. It would form stars. It would make clouds. It would show spectral lines. But it does not. So we infer it through gravity. That is both powerful and frustrating. Powerful because gravity is universal. Frustrating because gravity is weak compared to the other forces, and it does not tell us the microphysics directly. When we say dark matter, we are describing a role in the cosmic accounting, not naming a known substance like hydrogen. So what could it be? The leading candidates are new particles beyond the standard model of particle physics. WIMPs, weakly interacting massive particles, were popular because they naturally produced the right relic abundance in the early universe in some models. But decades of direct detection experiments have not found a convincing signal. Axions are another candidate. Very light particles that could be produced in the early universe and behave like cold dark matter on large scales. There are sterile neutrinos and other possibilities. There is also the possibility that dark matter is not a single particle species, or that it has self-interactions that are small but not zero, which could affect small-scale structure inside halos. Each candidate has constraints from cosmology, astrophysics, and laboratory experiments. And so far, no candidate has crossed the line from plausible to confirmed. Now I want to connect dark matter to dark energy, because the fate of the universe depends more on dark energy than on dark matter. Dark matter clumps. Dark energy, as far as we can tell, does not clump much on galaxy scales. It behaves like a smooth component with negative pressure. In general relativity, pressure gravitates too. Positive pressure adds to gravitational attraction. Negative pressure can produce repulsion in the sense of accelerated expansion. Observationally, we discovered the acceleration in the late 1990s using Type 1a supernova as standardizable candles. These supernovae have a known intrinsic brightness pattern. By comparing how bright they appear to how much their light is redshifted, we map the expansion history. The distant supernova were dimmer than expected in a decelerating universe. That implies the expansion has been speeding up for the last several billion years. We also see dark energy's fingerprints in the cosmic microwave background and in baryon acoustic oscillations, which are the fossilized imprint of those early sound waves, now seen as a preferred clustering scale in the distribution of galaxies. Combine these probes, and the simplest consistent model is a cosmological constant, a constant energy density of the vacuum. But I need to be careful here. Vacuum energy in quantum field theory is a complicated subject, and the naive theoretical estimates do not match the observed value. That mismatch is one of the biggest unsolved problems in fundamental physics. In cosmology, we treat the cosmological constant as a parameter that fits the data extremely well. Whether it is truly constant or a slowly evolving field is still open. Current observations are consistent with a constant equation of state parameter very close to -1, but the error bars still allow small deviations. So what happens to the universe in the long run? Dark matter will keep doing what gravity makes it do. It will clump into halos. Those halos merge hierarchically. They build larger structures. But dark energy changes the stage under their feet. As the expansion accelerates, distant galaxies recede faster and faster. On very large scales, the growth of new structure slows down because the expansion pulls regions apart before gravity can gather them. The cosmic web effectively freezes out. Locally bound systems remain bound. Our local group, including the Milky Way and Andromeda, will likely merge. Galaxy clusters will remain as islands, but beyond a certain distance, galaxies will slip beyond our observable horizon. Not because they move through space faster than light, but because space itself expands in such a way that light emitted now may never reach us. In that future, dark matter is not evil. It is the main mass component holding galaxies and clusters together. It is the reason halos have deep potential wells that keep stars from flying off. But it also sets the stage for some of the most extreme gravitational environments. In the centers of galaxies, supermassive black holes grow through accretion and mergers. Dark matter does not feed black holes efficiently by itself because it does not radiate away energy, but it shapes the gravitational potential that funnels gas inward. The interplay of dark matter, baryons, and black holes is one of the hardest parts of galaxy formation to simulate accurately, because baryons have messy physics like cooling, star formation, and feedback. Dark matter is simpler in many ways. It is usually modeled as collisionless particles in simulations. Yet even there, we still debate details on small scales, like the inner density profiles of dwarf galaxies and the number of satellite galaxies around Milky Way-like systems. Some of those tensions may be due to baryonic feedback. Some could hint at different dark matter properties. The honest answer is that we do not yet know. Let me run a thought experiment to keep this grounded. Imagine you could suddenly turn off electromagnetism, leaving only gravity. Stars would not shine. Atoms would not form chemistry. But gravity would still sculpt matter into clumps. Dark matter is closer to that gravity-only behavior than ordinary matter is. It does not cool by emitting photons, so it forms large, puffy halos rather than thin disks.